So all of these talking on top of a formulation doesn't really make sense. So let's look at it with some numbers. So let's see an example for designing a confinement and flexural strengthening for a column with large eccentricity. So we get back to the same structure that we had. If you remember, it was 2 bays, 3 frames, 2 floors. So first floor, second floor, left side, center column, right side column. And we get the actual forces from the analysis and the bending moments from the analysis. We calculated the formula which ACI suggested, and whatever is more than 10%, we have large eccentricity. We concluded in the previous example that only one of the columns had small eccentricity, the rest have large eccentricity. So for columns with large eccentricity, if NST, MST lies outside of NM domain, the actual bending moment interaction, therefore confinement plus flexural strengthening is required. What is this extra bit that we're calculating? Is just to make sure that we have large eccentricity. So we don't just trust the ACI formulation, we actually calculate the NM domain. We will get back to this NM domain, the actual bending moment interaction, in few minutes. Now, the structure that we have, I am selecting this column, for example, in the second floor on the right side. I have the dimensions, I have the analysis results, the applied actual force and the bending moment. I have the cross-sectional properties of my column. I have my material properties, the mean values of strain for concrete, the mean value of strain for steel. I have the factor of safeties, so I can quickly calculate the FCD, the design characteristics for my concrete, and the yielding design yield strain for my steel. I have some properties of the reinforcement as well, so I give or take know everything about my structure. So we're dealing with these numbers. Again, as I mentioned, these values are in terms of reaction, so if you want to use them, you have to change the sign. This is the cross section of the column that we're dealing with, as we just saw the values, and I have contacted the factory, and these are the properties of the FRP that they have provided me. I have the thickness, the width, the modulus of elasticity, and the characteristic strength of my FRP. Talking about the NM domain, or actual force bending moment, we followed that simple formulation from ACI to figure out whether we have large eccentricity or not. But the more scientific way is to calculate the NM domain for your section, which you can either do it by hand or you can use softwares to do it for you. Gala software is one of those powerful tools which simply, by just giving the properties of your cross section in terms of dimensions as well as reinforcement positioning as well as the strength of your material, it can show you the domain of your cross section. Now, if your points in terms of NSD and MSD are outside of this domain, then you have large eccentricity. If they're inside, then you have small eccentricity. We have a concrete section, so compression is strong, and these are the points for that NSD and MSD of that column that we have selected. As you can see clearly, they're outside. The first point is the actual force, and the other ones are negative and positive moments, bending moments. They're outside of my domain, so the section has large eccentricity. This is an additional step when you figured out that you have large eccentricity. Using that simplified formula, you can do the NM domain for that specific column that you want to do the analysis. If it's like this, not only confinement is required, you need to do it for flexural as well. So that long process of large eccentricity should be applied for designing the FRP around it. Now, as you notice, we select one trial in terms of how many layers we have to use, and then we calculate everything. If it was satisfied, then that number of layers is sufficient. If it wasn't satisfied, we go back to the calculation and we add more layers. Adding more layers will mean that the thickness, the total thickness, will be increased. Now I'm using one layer. The factory has told me that my layer will be 0.167 millimeters. So the total is the same, 1 times this thickness. I have the width of my FRP and the mechanical properties of it, which all have been provided by the factory. We are trying to do this, but we said because the calculation is a little bit sophisticated, we do non-dimensional values of both of these. We followed step 0, 1, 2, 3, 4. So let's start with step 0. We have to calculate μs, μf, NSD non-dimensional, MSD non-dimensional. All of the values that we have over here, we already have them. The only issue is FCCD, design strength of confined concrete, that we have to calculate. FCCD, if you remember, is very similar to what we did in the small eccentricity. So this was the formulation, the effective confinement pressure, which was F1 effective, comes back. The coefficients of efficiency, which consisted of coefficients of horizontal efficiency, coefficients of vertical efficiency, and coefficients of inclination efficiency, come all into play, exactly similar to what we did with small eccentricity. Some geometric strength ratio, to just put it in the formulation, elastic modulus, and then this was the FRP design strain, which was a minimum of either 0.4% or this bit of the formulation, which, if you remember, environmental factor, a partial safety factor, and this was the strain that we were getting from the factory characteristics. So the strength of my FRP that the factory has provided, and the elastic modulus of my FRP that the factory has provided. So now we have this, we have this, we have this, and we have this. So having those, we have F1 effective, we put it here. FCD, we have already calculated it by using the mean value of my strength and dividing it by the factor of safety. I can get the FCCD. Having the FCCD, I'm back in step 0. Tick, 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 tick. The rest of the values, I have already got them. It's very easy. Let's see. So mechanical ratio from step 0 for the tensile steel reinforcement. I have the D, I have the B, I have FCCD. I just calculated it in the previous step. And I have the area of my steel as well as the design yield strength of them. So μs, done. The same thing happens for μf, the mechanical ratio relation for FRP system. Now thickness of FRP, width of FRP, as well as the strength of my FRP. The rest of the ratio I have already calculated for the previous one. The width, the height, as well as the FCCD, which I followed exactly what I did for small eccentricity columns. So step 0 so far, 2 of them done. Anyhow, it's a time consuming process, but it's not a very sophisticated one. This guy done, this guy done. 2 left from step 0. The NSD is the actual force on my column. I already have it. And the bottom bit I have already calculated for the other one. So very simple. The MSD again is the moment on my column. So I just go back to my analysis and figure it out. I just put it. I have the non-dimensional MSD and NSD. So step 0 so far, okay. μf, μs, NSD, MSD. Done, 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 done. Now I'm trying to calculate this because this is already done. It's over here. The rest of these formulation will help me calculate this. Out of this massive formulation, I have done this. U, if you remember, it was the ratio of the tensile strength area over compressive steel area. Mi S, you have already calculated. This was the issue, and the etas were the issue. So let's go to step 1. Step 1 simply says calculate an eta for yourself. You have this value, you have this value, you have this value already calculated in step 0. So from step 0. And then you just have to calculate U. So in terms of U, usually we have symmetric reinforcement distribution in a column. So whatever area of reinforcement is in compression will have the same area in tension as well. So the ratio of their area will be 1. U is the ratio of reinforcement steel in compression to steel in tension. Because we have the same distribution of reinforcement, U is 1. So step 1 done. Now we get to step 2, which, if you remember, we were calculating boundaries and ranges for those etas. Eta 0, eta 1, eta 2, eta 3. We looked at the formulation and we nearly have everything except R. R had this formula and the issue was this. This was the biggest challenge that we were having in all of these calculations. So it's a minimum of either this or this. This bit, environmental factor, partial factor, epsilon fk, which you were getting it from the factory results, so all done. This bit was this issue, which was FFD2, which was representing the mode 2 of the debonding over the elastic modulus of FRP. The problem was that this FFD2 had a massive formulation. Now, all of the values needed in this formulation are here. We just simply put them in, we get the value. This is KB formula as well, which, as you can see, is the width of the FRP to the width of the cross section. So this one was calculated, was here. All of the other factors have been calculated here. Now I got this, I put it here. I know the elastic modulus of my FRP. The factory has told me I have these two values. The formula says the minimum of these two values. So clearly this is smaller. So I put this over here and I figure out R. Having R, having U from the previous step 0, Mi S and Mi F from step 0, I can calculate the boundaries. Eta 0, eta 1, eta 2, eta 3. If you remember, step 3 was to just compare that eta that I have, which I calculated in step 1, to the eta ranges that I had from step 2. Which value is this between? Exactly, it's between eta 2 and eta 3. So in this case, the failure is because the FRP has ruptured as well as the steel has yielded. So 1B, steel yielded, FRP has ruptured. Now based on that, I have a formulation for this, which is, again, I have calculated all of those etas. Eta 1, eta 2 are already calculated, and I have also calculated my eta in step 1. So I can just calculate this. Let's do it. And it's this value. And now we just simply go back to the formulation that we had in the beginning, the non-dimensional flexural capacity of strengthened member, considering the actual force that you have on it. Mi S, Mi F, and U were calculated from step 0, and I just calculated this bit of the formulation considering my eta and the ranges that the eta had. And this is the formulation, so 0.090, 0.090. I just put it in, I got a value. I compared this to my non-dimensional applied moment. Unfortunately, it's smaller, so it's not verified. Now I have to do all of the calculations again by adding more layers. Now, initial guess was 1 layer. with that thickness, this was the thickness. Now I say, okay, I add another layer as well. So now instead of having one layer's thickness, I have this times 2. A new thickness is produced. I calculate everything, which TF was a player in it. For example, μF was a mechanical property of FRP, so TF had an effect on it. And hopefully this time it will be satisfied. Now, so far we talked about FRP for beam, for flexural and shear, FRP for column, for confinement, as well as if there is large eccentricity for confinement, as well as flexural strengthening. Now, the point is, the joints that these beams and columns get together are important as well, and sometimes they don't have enough shear strength. One of the biggest issues that we have in failure of concrete sections is that the lateral force of the earthquake cuts those joints, and the slab cuts the joint as well. So FRP is also used for improving the joint shear strength. To apply it is a little bit hard. As you can see, you have to open the walls and the beams to get access and wrap it around them. In this case, as you can see, only the joints are getting FRP wrapping. It's a very sophisticated process to apply it, but once it's applied, you have very good performance out of those joints. This is probably a school or a hospital that they're retrofitting. There are different ways that you can apply depending on the situation. As you can see, the joint should be completely exposed. You apply the FRP, then you cover it and you fill up the walls as well as the slab. To calculate it, depending on whether you are an interior beam column joint or you are an exterior beam column joint, these two formulation exists. These are for calculating the capacity that you have, and that should satisfy this formulation, which if satisfied, there's no need for shear strengthening of beam column joints. I have given you the description, all of them, in case one day you need to calculate that. It's based on Eurocode 8. And now, if it's not satisfied, let's say that you calculate your applied shear at the joint and it's not satisfied with the resistance or the capacity of the joint that you have, then when you add FRP, a bit of FRP in terms of shear capacity will be added to your resistance. So simply the same formulation that we had before, if it's not satisfied, we add some shear capacity from FRP, which simply is this formulation: area, strain, elastic modulus. And then hopefully the formulation will be satisfied. Now, to end this lecture, let's just look at some case studies that we have modeled FRP for some school buildings. Two case studies, a 2-story and a 3-story. This one just has 2 classrooms. This one has 15 classrooms. We have modeled it in full 3D with the highest details possible, having access to the detailed drawings and the plan of the structure. The models comply with that in terms of material and in terms of the cross-sectional properties. Now, we analyze the schools as a simple pushover analysis, and this line, the bottom line, is the, let's say, original building. Now, adding the FRPs only to the columns, as you can see, we have a little bit improvement in terms of strength, and then a little bit improvement in terms of ductility, and we have shifted the failure. Let's say if this is the failure, this is the damage limit state for complete collapse, which was at this point, let's say 2.8% of roof drift. Now we have taken it to 3.5%, or in this case much more improved, from 1 something to 2 something. So FRP has improved not only the strength Also, it has added some ductility to the structure, so the failure, the complete failure, which is very dangerous for a school where the next generation of the students are studying, has been shifted away from its previous capacity. We applied like thousands of earthquakes to the same building. The red ones are the FRP retrofitted one, the blue ones are the original ones. Every single dot represents a performance point. Remember, if you apply, for example, an earthquake through N2 method, for each earthquake that you apply, you get 1 performance point. So each of these are, I think, 1,000 earthquakes with different scalings have been applied, and out of those, fragility curves will be developed, which again, looking at the fragility curves as well, clearly the FRP ones have shifted away the performance of the structure in a better way. So if before the building had 50% chance of failure at an earthquake of 1G, now it has 50% chance of failure at an earthquake of, let's say, 1.3 or 1.4G, which is much better.